This is our second video from section 16.2 on line integrals. Hopefully if you're watching this now, you've already seen the first video where we've touched on what it is that a scalar line integral is computing, how we can set up those integrals, and it kind of touched on the theory of, how we set these up and how they work. But theory's all well and good, but if we can't do this in practice, it's maybe not the most useful. So let's see if maybe we can get a couple examples going of the scalar line integral, and also along the way I'll try to build some of the other line integrals that maybe we might need to work with later on. So, shall we? Example number 1, I'm having you integrate this scalar function on this line segment from the point 200 to the point 540. Okay, so basically what's being asked of here is we would like to evaluate this scalar line integral, okay, of the form we integrate over C, f ds, and for the f here, I want that to be the function that I'm integrating, and for the C, I want this to be the curve that I'm integrating over. Now, some comments on how we set this up, setting up our bounds, rewriting our function, and actually rewriting our differential. We're actually going to need a parameterization for our curve before we do any of these things, right? So the very first step that I'm going to take here is that we need some sort of parameterization for this curve, or for this line segment, C. Now, I'm going to dust some stuff off here. I'm going to have us try to use this parameterization. I will set up this vector here. Let's say 2 plus 3t, 0 plus 4t, and then 0 plus 0t. Now, maybe it might seem that I've pulled this out of nowhere, but I'll explain where this came from and why this is kind of a shortcut for a lot of the line segment examples that we're going to use. Oh, and I'll go ahead and conclude this here. I'll give you the interval that goes along with it too. We'll try this on 0, 1. Now, if this came out of nowhere, just refresher, for a line, what we are going to, let's fix my pen blurb here. For a line, you are going to need a point on the line, and as long as you have a point on the line, you'll also need a direction vector. Okay, so plus a direction. Here's how I basically set up every single one of these coordinates. I picked our starting point, and then the coefficient that I had to tack on here was basically how far I have to travel to get to my next coordinate. Okay, so how far to the next coordinate. You notice that the difference from 2 to 5, I had to travel 3 units there. And then that was what I was multiplying by t. Okay, and that trick that I applied, I did this in every single coordinate. Okay, so I start at 0, I have to go 4 units to get to the next coordinate, hence my 0 plus 4t. I start at 0 here, and I have to go 0 units to get to the next coordinate, hence my 0 plus 0t. And then here, the interval that I'm using, if you try this method, I'm basically just by default going to use 0, 1. So this here is basically going to be a shortcut for my line equation. Okay, so this is a shortcut for my line parameterization if you're given 2 points and you need a line segment. Okay, now you can go ahead and do this the way that we had set this up before. Find your direction vector, find your starting point on the line, yada yada. You can do trial and error to figure out what sort of interval you need to work this on, or this is kind of a shortcut for our setup. Okay, now this is kind of a messy looking line parameterization, so I can clean this up a little bit. Okay, this is going to be the same exact thing if I get rid of all of the clutter, okay, all the needless zeros. This will look like 2 plus 3t comma, 4t, comma, 0. And again, my interval hasn't changed here, okay? And if you are wanting to double check this, you know, we start out at or t equals 0, you do get the 0.200. You plug in 1, you do get the 0.540. All right, so we have got our parameterization for C. Check mark. That is taken care of. However, I do need to set up the rest of this integral, right? 3 things that I had told you guys that we need to fix. We need to, you know, rewrite our bounds on the integral. I can't just integrate against C. I need to rewrite my function. I can't leave this in terms of x, y, and z. And I have to rewrite this differential because I don't know how to directly integrate against arc lengths, okay, algebraically. How does that work? We have to rewrite this. So I'm going to go ahead and tackle what it looks like if we fix each of those things, okay? Now, first off, for my bounds, I've mentioned before, we want to steal the interval from your parameterization, right? So if I'm looking to steal an interval from a parameterization, well, there it is right there. We're just going to use 0, 1. Those will be the bounds on our new single variable integral. The next thing that I'm going to go ahead and do is try to fix my function. Okay, now just for reference, I'll scroll back up to copy this down. We had x minus 3y squared plus z. Okay, x minus 3y squared plus z. What I want to do is sub in your parameterization, right? So substitute in your parameterization to get what I'm going to call f of r of t. Now, this maybe looks a little bit weird because in my original function I have 3 slots for input, but I'm only writing this like I'm plugging in one thing. But keep in mind, that function for your parameterization has 3 components. So what I'm really substituting in here is subbing your x component for your x component, sub in your y component for your y component, and sub in your z component for your z component. So we do not want to leave this in terms of x, y, and z. We want to replace my x with 2 plus 3t. We want to replace my y with 4t, and we want to replace my z with 0. Okay, and if you want to, you can go ahead and clean this up. So this is the same as 2 plus 3t minus, here if I clean this up, that'll be minus 48t squared, because 3 times 16 is 48. Okay, that fixes my function. The final thing that I'm going to want to do is fix up my differential. Okay, so that differential that goes on the end, what I have said before is if we're trying to replace the ds from a line integral, the replacement for my ds is basically going to be the magnitude of r prime of t with a dt thrown on the end. So this is very plug and chug. You have to look at whatever parameterization it is that you started out with in the first place, and that is what we're using for the r that we reference right here. Okay, so this is why I said at the very beginning of this problem it was very important that we get a parameterization first, because we needed it for every single one of these steps. If I go to plug and chug this here, the first thing that I will need to do is take this derivative of my parameterization, your derivative of 2 plus 3t with respect to t, you'll just get a 3. Your derivative of 4t with respect to t, you will just get a 4. And your derivative of a constant is always 0, so we'll get a 0 on the end. So I need the magnitude of that with a dt slapped on the end. My magnitude formula is basically going to look like, you know, square root 3 squared plus 4 squared plus 0 squared. Hopefully we've seen 3, 4, 5 right triangles often enough to recognize that this is going to be 5 units long. Okay, so there, let me actually not forget the dt on the end. Okay, so this is 5 dt. That's what my differential gets replaced with. Okay, so if I piece all of this together, again, we were trying to rewrite trying to rewrite this line integral of f over c, we just said the bounds were supposed to be stolen from the parameterization. Those were going to be 0 and 1. My function, when we fixed this, okay, substituted in the parameterization, we said that we would get this polynomial back. And then my differential, we said that we were going to replace ds with, after we cranked out that magnitude times dt, this thing is being multiplied by 5 dt. And at this point, since I did ask for evaluation, we can clean this up and try to antiderive and solve. I'm going to go ahead and just pull that constant out front of this integral and then worry about antideriving everything else, okay? Your antiderivative of 2 is just 2t. Your antiderivative of 3t is going to be 3t squared over 2. And your antiderivative of this last term, this will be 48t cubed over 3. This is all evaluated between 0 and 1. Or if I go to clean all of this stuff up, 2t plus 3t squared over 2, this last bit actually reduces, so I don't have to have a fraction there. And then you substitute in the top number and subtract off whatever happens when you plug in the bottom number. Plugging in 1 to this polynomial just gives you all of the coefficients back. Okay, and I'm not super worried about the algebra here. Y'all know how to add and subtract fractions. So if I'm looking for evaluation, just simplify whatever that result is. Okay? Now, some notes here, because some of you may have been wondering, back on this step, when I picked this parameterization for my function, right, I said, hey, let's try this thing. Some of you might remember that when we were setting up line equations way back in the first test unit, that representations for lines, they're not unique, right? We could get two totally different looking line parameterizations that represent the same line if we're just starting at a different point. Maybe I could have used 540 as a starting point. Or if you use a scalar multiple of your direction vector, right? I here used 340, but I could have easily used -3 -40. Or I could have used 680, that's a scalar multiple. That would give me a totally different line. Maybe it would change up the interval that I needed to hit these points at start and end, but it would have been a totally different looking line. Now, before we move on, I do want to point out that alternate parameterization would have actually been okay. So just a remark, curve parameterizations aren't necessarily unique. Sometimes there's, different ways that you can represent the same curve. That is totally fine, but the one catch is that you have to make sure that you traverse that curve in the same direction. So if I specify a starting point and an ending point, we actually better start where we say that we start and end where we say that we end. For an example, I've got these two curve parameterizations here, R1 and R2. A comment that we can notice about both of those, they have the same x and y coordinate. So this is basically, hopefully, going to lie on the line y equals x. Hopefully that should be clear, because your y and x are the same. And the starting and end point here are specified in this first curve by 1, 2. So that means if you plug those t values in, we start at 1, 1 and we end at 2, 2. Notice for the second curve, if I plug 0 in, e to the 0 is 1. If I plug log of 2 in, my log and exponential rules imply that that gives me 2 back. So this also starts at 1, 1 and ends at 2, 2 and travels that same line. If you used both of these parameterizations, okay, and integrated against them, you would basically get the same result, okay, for using these for the same c. Maybe your integral for the second one might look a little bit more complicated, but ultimately you'd get the same result back. Okay, your choice of parameterization doesn't matter as long as you still get the same curve and the same start and end point. another comment that I'm going to go ahead and make as far as setting these things up. The original theorem or setup that I gave for you guys deals with when you have a singular curve that you're traveling along, but maybe that's not always the case. So you'll see in this particular example, it kind of looks like I have maybe 3 wedges that of this curve, or 3 portions of this curve that I'm traveling along. This kind of looks like a piecewise function. What I'm going to go ahead and note in this particular example, if you have a setup like that for your curve, as long as you're not jumping points, if you can actually trace this from start to end without lifting up your pen, this is okay. You can split up your integral to compute this if need be. So what this situation would suggest is if I had a line integral to work with, another way that I could set this up is just integrate over each of the pieces and then sum this together, right? So I could think about there as being an integral across the first piece, plus an integral across the second piece, and then plus an integral across the third piece. You may remember from Calculus 1, there was a technique that if you had an interval and a bunch of piecewise functions, you could break this up in kind of a similar manner. This is the same exact principle, except for instead of breaking up an interval, we're breaking up a curve. Now, I'll go ahead and do an example to highlight what I'm talking about here, at least, set this up. I've got 2 sort of curve sections here. Let's go ahead and think about this. Let me change my color. I'll think about this as a C1 and as a C2, right? So here, if I wanted to draw some parameterizations up, these are both types of curves that we've seen parameterizations for before. For my C1, what I will go ahead and suggest that we try doing is that same sort of trick that we set up before. Here, if I do starting point plus whatever quantity it takes me to get to my next coordinate times t, this is basically going to be 0 for my x component because I'm at the origin, plus 1 times t. Okay, so I'll basically get a t here. And then for my y coordinates, again, since this is the origin, 0, 0, I start at y coordinate 0, but I also end at y coordinate 0. So if I did 0 plus 0 times t, we're just going to get a 0 here. Okay, and then the trick that I used before, that trick, always use the interval from 0 to 1. Okay, now for your C2, if I want to set that guy up, this looks like, and we've seen a parameterization of the circle before, circles, as long as you're traveling in the counterclockwise direction, you should be able to get away with using cosine t, sine t, as long as you pick appropriate angles to match where you're traversing the circle. Okay, now, those coordinates represent the unit circle. We only care about the section of the unit circle between the angle 0 and pi, so the interval that I'm going to want to pick here goes from 0 to pi. Okay, now if I wanted to set up my bounds, my function, and my differential here, I don't want to do it where I'm working with c, because c is the whole curve and we just split this thing up. So what I'm going to go ahead and do is split this. Right? I said that instead of integrating over c, we may as well integrate over each of the pieces. So here's my c1, my first portion of my curve, and my c2, my second portion of the curve. And now I get to apply that trick, okay, for converting this for each of these curves, right? Now, just as a refresher, if I want to fix my bound, okay, on this first integral, we said that to fix the bounds, you just steal whatever interval it was that you used for your parameterization. So I'm going to integrate from 0 to 1 here. To fix my function, we have said that you want to actually substitute in, get rid of your, x's, y's, whatever. That means I want to substitute in the x coordinate from my parameterization. Now, since I was dealing with C1 in that integral, I look at the C1 curve and what x was supposed to be there. This is going to be 2 plus t. I replace x with t here. And then as far as replacing ds, we have said that we replace ds with the absolute value of r prime of t dt. And I'm just going to write that out now, so we'll worry about computing it in a moment. Okay, so really I'll label these to keep them separate. Just to be specific, I don't just want, any old r. This needs to be the one that represents C1. So this is going to be R1 prime of t dt. Okay, let's go ahead and fix the second integral up. Okay, if I'm worried about the bounds here, replace the bounds with whatever bounds that you used for C2's parameterization. We used 0 pi, so we're going to replace that with 0 pi. Next thing that I need to do is fix up my function. If I am fixing up my function, I need to replace x. And what do I replace x with for curve 2? I replace it with the cosine function. So this is going to be 2 plus cosine of t that I'm integrating against here. And then as far as replacing my differential goes, okay, same deal. We want to make sure that we replace the differential with an r prime of t in a magnitude, okay, dt. But again, this was curve 2 specifically. Make sure that when you do this, you're dealing with r2. So I'm going to go ahead and worry about evaluating this, okay? If I crank through this here, for that first curve, actually let me scroll up so we can see this. If I'm worried about R1 prime, well, R1 with t comma 0, the derivative of that is just 1 comma 0. Now for this other function, okay, if I'm trying to worry about R2 prime, well, R2 was cosine t comma sine t. My derivative of that is going to be minus sine t comma cosine t. That's the magnitude that I am taking, there. Let me get that t squeezed in there. Now, as far as evaluating this, well, here, my magnitude of the 1, 0 vector, you can sit there and shove it into the square root formula all you want, or you can note it's only a unit long. Okay, so that's just going to simplify down to 1. That thing is 1 unit long. Over here, if I try to clean up my magnitude of that derivative vector, we're taking the square root of basically sine squared t plus cosine squared t. And hopefully if you're up on your trig identities, sine squared t plus cosine squared t is 1. We square root that, we get 1. Basically, both of those in this particular example, they didn't really do anything, right? So we are just worried about taking an antiderivative of 2 plus t dt plus its integral from 0 to pi 2t plus cosine t dt. Okay, so both of these are now single variable integrals. This is pretty standard calculus 1 type stuff. I'll get 2t plus t squared over 2 evaluated between 0 and 1 for this first integral. I will get, oops, sorry about this. I just noticed a minor error here. I copied myself an extra t where I didn't need one. I was wondering why this looked a little bit strange. Sorry about that mistake there, guys. So same function that we're integrating, right? Not a different one. Here, if I antiderive 2, it's the same 2 that I antiderived before. I'll get 2t. Plus a cosine t antiderived, so basically plus a sine t on the end. We're evaluating between 0 and pi. And if I go to evaluate these things, this first piece, I'm just going to get 2 plus a half. Because when you go to subtract off what happens when you plug in 0, you're subtracting off a 0. Over here, on the other hand, I will get 2 pi plus sine pi. Sine pi is 0, minus what happens when I substitute in 0, and that also is pretty uneventful. Okay, so ultimately here, what I should be looking at is 5/2 plus 2 pi. Okay, that's my end result. Now I'll try one more of these scalar line integrals here. All I'm just going to ask is that we rewrite this one. Okay, so let's just rewrite this one in terms of t. I'm giving you a curve that is a section of parabola here. Go from, let's pretend that's minus 1, 2 to 2, 8. Okay, so here's my curve C. Now, comment, this is not given in terms of a parameterization R of t. It's just a standard plane curve. So I wanted to mention kind of a cheap trick for your parameterization of plane curves. Okay, so parameterization of things of the form y equals f of x. If I wanted to parameterize this, you're going to need basically some sort of x coordinate and then some sort of y coordinate, right? So basically what I want to think of is x comma y. Now I'm doing this in terms of t, so really instead of having something like x comma y, you know, that doesn't match up with my variables, let's think about this, right? Instead of x comma y, we know that y is really equal to f of x, so let's use f of x in its place. That gets rid of one of my variables that I don't want, but I still have this pesky thing in terms of x, so let's not use x, right? Instead of x comma f of x, let's try t comma f of t. It's the same pattern, but it puts us in terms of the correct variable. And the only catch that I need to work out for here, if this is a plane function, we said that we needed to start at the right spot and end at the right spot. You start with an x-coordinate of -1 and you end with an x-coordinate of 2. So steal your x-coordinates, right? This is going to go from -1 to 2. Now, I ask that we rewrite this thing. Rewriting this thing calls for us to fix our bounds, our function, and our differential. If I'm fixing my bounds, we have said that we steal the interval that the parameterization lives on. If I am fixing my function, we have said that we go to plug in the x, y, and possibly z coordinates of our parameterization to our function. Instead of x, we use the x component, which is t. So this means t squared. Instead of y, I'm going to use my, f of t. In that particular case, f of t here, if you don't like saying f of t, or, here, y, f of x, that's the same exact thing that I'm trying to get across here. F of t in that case is just going to be 2t squared, right? So here, I'll go ahead and fill that in. Okay, instead of f of t, we really want 2t squared. That's my y coordinate here. So replacing my y, here's my 2t squared. Instead of ds, we want to tack on r prime of t dt. Well, take the magnitude of your r prime first. So if I go ahead and clean that up, your r prime in this particular case, okay, I'll go ahead and simplify this. This will be a 2t to the 4th over here. My magnitude of r prime is really going to be my magnitude of 1 comma 4t. So ultimately, the integral that we would be worried about cleaning up here is 2t to the 4th times square root of 1 plus quantity of 16t squared. Okay, and since I don't really want to have you guys dealing with like trig substitution or anything crazy right now, I'm going to go ahead and leave it at this. Okay, all I asked for was just set up. So we're good to rewrite this and stop here. Okay, now those were scalar line integrals, and before we move on to vector field integrals, I said that was our motivation from the work section. There are 3 more common differentials that we may use for scalar line integrals. Now, for these other differentials, these are different line integrals or different types of line integrals for what we've been doing, where we aren't necessarily integrating against arc length s. The 3 other ones that we might see, and these are actually maybe kind of comfortable looking, dx, dy, and dz. Now, these look kind of like what we're used to back in the triple integral and double integral section. Why are these like super new? Now, notice we're still dealing with line integrals here, so you would still probably see a setup where you're integrating against a curve C, and we did not integrate against C when we were dealing with double and triple integrals. That means that we still need to fix stuff, including my bounds and my function and my differential. Okay, so since these are scalar line integrals, fixing the bounds and fixing the function, we're still going to do the same exact technique that we did before. You know, steal the bounds from your parameterization, plug in your parameterization, but the differentials are going to be different. Replacing these differentials, we didn't really have to do this for double or triple integrals, but we do for line integrals. Okay, I'm going to replace, anytime that I see it, my dx with x prime of t dt. I'm similarly going to do dy anytime I see that. That is y prime of t dt. And my dz, this is the same thing as z prime of t dt. And what I mean by this, I'm assuming my x, my y, my z, okay, where these x, y, and z, these are from my parameterization, right? So I'm assuming that if I say x, y, or z, this is where these things are coming from. I keep saying that when we substitute, we're replacing an x component with an x component, a y component with a y component, and so on. Basically, we're just stealing these from my parameterization. And if you're wondering where the heck these things came from, these are basically your differential formulas from Calculus 1. Okay, so these formulas, okay, Calc 1, I can barely fit this thing on my slide. You guys might have seen something like dy is f prime of x dx. These are the same exact formulas. We're just switching the variables around. So here, if I wanted to try an example here, I'm actually not going to necessarily think too hard about the end result. I'm mostly focused on the setup. If I want to evaluate this thing with this parameterization on this interval, how do I do it? Well, I mentioned before, my bounds. If I'm worried about setting up my bounds, this works the exact same as the other line integrals that we were doing. We are going to steal whatever the heck bounds came from your parameterization. My function, fixing my function, okay? Same deal as usual. I wanted to sub in my parameterization to fix my function. What I'm going to get there is that this x squared plus y squared, this is going to turn into, okay, so I'll put an arrow here. If you sub in cosine of t for the x coordinate, you've got a cosine squared. And if you sub in sine t for the y coordinate, you've got a sine squared. Now, as far as my bounds or my differential on the end, we have said that dy is supposed to be y prime of t dt. You'll notice that my y here was sine of t, so my y prime is going to be cosine of t. If I piece all of this together, we have just said, okay, my new bounds are 0 to pi over 4, my new function, this is going to be cosine squared of t plus sine squared of t. And my new differential that I get to throw on the end here is going to be y prime of t dt. So just cosine t dt. Now notice with those differential formulas, there were no more absolute values. I don't have to worry about that anymore. This is just a straight up cosine on the end. Okay? And if I go to clean this up, please don't forget your trig identities. You know, that whole thing just simplifies off to 1. So I'm going to go ahead and just anti-derive cosine terms here, which means I'm evaluating sine between 0 and pi over 4, or I'm just going to get root 2 over 2 minus 0 back, right? So root 2 over 2 here. Looks totally different from our original integral, but you do have to keep in mind, you know, I'm not integrating with respect to y over an interval, so I can't just, you know, x squared y plus y cubed over 2. We're not doing that here because I've got to integrate over this line. Okay, so we do have to treat this like a line integral and utilize our parameterization here. Now, the reason that I bring up these new differentials, okay, so the reason that I'm talking about this dx, dy, and dz, frequently, something that you may see a lot is doing multiple of these at the same time, okay? So last time I just gave you an integral where we were dealing with a dy. You might see a dx and a dy and a dz at the same time. Now the idea behind that, and this touches back on our idea of computation of work in a vector field. I said that, you know, in the last lesson, we might want to figure out how to integrate a vector field over a curve if we're worried about, you know, trying to take a force times a distance, but extrapolating it with integrals. The reason that we might see this in multiple, you know, of these integrals paired together is it's kind of like we're breaking apart a function into an x component, a y component, and a z component. So if I had wanted to compute work by integrating a variable force, well, if we're in a vector field, what we could try to do is break up what force is happening in the x direction, find the work there. What force is happening in the y direction, find the work there, and what force is happening in the z direction, and find the work there, so that ultimately you could actually sum all of these things together. Now, we could write the integral in this format, or if I want to, I can abbreviate this. You know, if it's clear that we're dealing with x, y, z coordinates, you can rewrite this without those variables tacked on the end. Or instead of treating this as 3 separate integrals, I could just slap them all under the same integral if they are all integrated against the same curve. So I just grouped all these together into one piece. Now, comment on the setup here and why I was tying this into vector fields. You could make the observation that this really looks like we're integrating a dot product. Right? If I took P, Q, and R as these functions that were components for a vector, and then I dotted them with this vector of differentials dx, dy, and dz, what this really looks like here is this thing looks a lot like my vector field. I'll call this F for now. P, Q, R. Okay? A vector field was nothing more than a vector function that you plug in, you know, a 2D coordinate and get a 2D object back, or you plug in a 3D coordinate and you get a 3D object back. Now, if this P, Q, and R were the same as these guys, P, Q, and R were functions of 3 variables, that means that this vector field would be a function of 3 variables, and we obviously get a 3D vector back. Now, this thing on the end, here, what I typically do is, let's kind of rename this. I'm going to rename this as a differential, a specific differential, a vector differential, dr. Okay, so what it really looks like I'm doing is I am integrating a vector field with respect to a vector differential, which I'm going to abbreviate as dr, and we put the hat over it to let us know that that thing looks like a vector. Now, some comments. This is just going to touch on exactly what I said above. If we've got this vector field that came about from these p, q, and r functions, what I just expressed that above integral as is, here is my f, okay, and here is my dr. So the compact way to express this vector field, integral that we're taking, that p dx plus q dy plus r dz, the compact way to do it is just say f dot dr. So this is a line integral because we are still integrating over C here, over a curve C. This is a line integral of a vector field, no longer of a scalar function, okay? How the hell do I rewrite this? Now some comments on rewriting this. Again, for all these line integrals, fixing your bounds and fixing your function is pretty much the same as before. You are going to need a curve parameterization, so you are going to need some sort of r of t to parameterize that curve, okay, on some sort of interval, and you steal the interval for the bounds, you sub in the parameterization for your function. That's totally the same. The new thing that we need to figure out is how to fix the differential. Now, as far as fixing the differential goes, this dr, here's some side notes on this. This dr, we just said this is dx, comma, dy, comma, dz, stuck inside, a vector. In the previous page of notes, we just said that you could use Calc 1 differentials to rewrite each of these things. So x prime of t dt, y prime of t dt, z prime of t dt. If you want to, we can kind of simplify the way that we express this and not have to write dt so many freaking times. I'm going to go ahead and just kind of factor that thing out. We'll pull this out and write it on the outside of my integral, of my vector here. And then if I really, really want to write this in shorthand, you notice that the x, y, and z, we assume that they come from the parameterization. If I'm taking the derivative of each of those in their respective slots, the shorter way for me to write this is just to say r prime of t, okay? So keep in mind here, what that is really saying is any time that you see a dr, this is really take the derivative of your parameterization and tack on a dt. Now, here's kind of where we summarize all of that again. If I go to rewrite one of these f dot dr integrals, there are three things to fix. I still need to fix, my bounds. I no longer want to integrate over a curve. Steal the interval from your parameterization. If you're integrating this vector field f, make sure that you fix it by plugging your parameterization in. And if you're, integrating with respect to this r differential, please rewrite that. Okay, you can't just leave the dr. Replace it using your parameterization. Take r prime of t and tack a dt on the end. And a comment, I know I talked about the setup for this specifically in terms of 3D, but the formula works the same. Okay, so if you have a 2D parameterization and a 2D vector field, roll with it. You're still making the same substitutions. You're still doing a derivative times dt to fix your differential. You're still sealing the interval, so that still works the same. Okay, I'll go ahead and touch on an example here. Okay, where we can go ahead and set this up. F dot dr, I've got my parameterization, I've got my interval. let's go ahead and put that in practice. We've said that we steal the interval. We have said that we substitute, okay, my parameterization into f. So I'll go ahead and note that here. I'm basically substituting in cosine t and sine t. I want to explicitly spell this out so y'all can see where I do this on the next round. And then I want r prime of t dt on the end, so I got a minus sine t cosine t dt on the end. This is me fixing my bounds, my function, and my differential. Okay, so each of those three pieces. Now, if I go to plug cosine t comma sine t into my differential, here's what I'm getting. Cosine t had to go in for x whenever I saw it, so there's my cosine t. And my sine t has to go in for y wherever I see it. So this is cosine t, sine t in the first slot, and a sine squared t in my next slot. Now here's the weird thing about my vector differentials here. You notice we didn't really have vector differentials before. You know, we just had the scalar things. And you may have noticed that I keep putting this dot in the middle of these integrals here, you know, f dot dr, and I keep saying f dot dr. That actually is a dot product, right? So I wouldn't keep saying dot if I didn't actually mean a dot product. So to evaluate this integral, you actually have to take that dot product, right? So the way that we do dot products is multiply component-wise. This means that first pair of x components, I will get minus cosine t sine squared t. If I multiply out my y's, I'm getting a sine squared t cosine t. Y'all may notice these cancel out. So ultimately, the integral that I'm taking is just of 0. And if you're trying to find the area underneath the y equals 0 curve, you can integrate and try to, but ultimately, you're just going to get 0 back. Okay? I'll do one more of these just so you guys have another example under your belt for these differential things. Here I'll try one more, okay? I need to fix my bounds, my function, my differential. If I fix my bounds, okay, my bounds, I'm just going to steal them from my parameterization. 0 and 1 here. For fixing my function, you have to substitute in each of the x, y, and z components from your parameterization to your function. So e to the x is no longer e to the x, it is e to whatever x is in your parameterization. I've got e to the 2t. My y squared is no longer y squared, it's the square of whatever my y component is, so this will be t squared squared. And again, x is no longer x, use 2t. Z is no longer z, use 5 instead. This is minus a 5 cubed that I've got in the end. We have said that to fix my differential, I need to take r prime of t dt. Well, that means I just need an r prime on the end, so here is 2t, and 0 dt. Now, there is some cleaning up we can stand to do here. You know, e to the 2t, t to the 4th here, 2t minus 125 over here. But before you actually antiderive or evaluate this thing, again, you have to reconcile your dot product. Actually take that dot product to simplify, okay? So if I take that dot product, my first pair of components gives me a 2e to the 2t. My second pair of components gives me a 2t to the 5th. And then my last pair of components, I get a 0 on the end. Okay? So, ultimately here, I'm boiling this thing down to a single variable integral. I'm going to get e to the 2t plus 2t to the 6th over 6, evaluated between 0 and 1. Or we'll get e squared plus 1/3 minus what happens when I substitute in 0. This is going to be 1 plus 0 here. Ultimately, I get e squared minus 2/3.